Hi everybody, and welcome to tutorial 2 in this series on HappyBrackets. I'm Garth Payne and I'm a Professor of Digital Sound and Interactive Media in the School of Arts, Media and Engineering, and also a Professor of Music Composition in the School of Music here at Arizona State University. Today we're going to run over several things. We're going to do a short refresher to look at the sound player object, the gain object and the envelope object, and then we're going to move on to playing samples. We're going to look at sample selection and sample playback and manipulation, such as altering the loop start, loop end and pitch of playback variables, and then we're going to move on to look at granular synthesis, granulating sound samples in real time. Okay, let's get started. For this tutorial you will need the folder tutorial 2. And as you will see, there are a bunch of patches in there, some exercises for you to do, and then some additional patches in other for you to explore later. So the very first thing I want to do is to revise some of what you looked at in the last tutorial. Here is a very simple patch that uses a wave player, a gain object, plugs the wave player into the gain object, and outputs that. So let's recreate that. In order to make that here in tutorial 2 folder, first of all we select the folder and then we will go new HappyBrackets sketch and let's call it lesson 2. You'll see, as you saw in the last tutorial, that this opens up a HappyBrackets action for you with this name lesson 2, and it already places it within the tutorial 2 package and imports a number of things for you so that HappyBrackets works. You'll notice that over here I have my HappyBrackets window already open. You can close and open that here. And you'll also notice that down here I have the documentation window open. I'd like to remind you that you can go up to View and select Quick Definition in order to open this help window that appears down here. Then as we go and write code in here, you'll see the variables that can be used. So let's make a new wave player. You'll see that IntelliJ already suggests wave player. I'm going to just call it WP for now, and we'll instantiate a new one, new wave player. And you'll see here in the help window that we have a number of options for instantiation. We're going to choose the last one, which is to give it a frequency and to tell it which buffer we're drawing on. So I'm going to make this 300. I'm going to put an F there because it's a float, and then a comma, and then I'm going to type buffer, and you'll see that it comes up with a bunch of different buffers here. I'm just going to use the sine wave for now and finish off that line. Now we have a wave player. So let's make a gain object. And you'll see that the gain needs to have a number of possibilities here, but the one that we want is in and outputs and a float, which sets its value. So we want to have one input and we want to set it at 0.2. Notice that every time I put in a floating number, I type the letter F afterwards to make sure that IntelliJ knows I want a float there. Now we're going to plug the wave player into the gain object. So we take the gain object, we add an input to it, and then we put the wave player into that input. Now the wave player is connected to the input of the gain object. And now we're going to plug the gain object into the output hardware of the laptop so that we can hear it. So hp.sound and plug the gain object in there. Okay, so now we have a complete piece of code, wave player, gain object, we've plugged those two together, and then we've put the gain object into the output hardware. So let's recompile that. Now we need somewhere to play that, so I need to go and start the HappyBrackets simulator. It'll start up here and you'll hear it beep. There we go. And so now we can send this code over here by either clicking on send here or right clicking here and sending it out this way. Let's just right click. And there you should be able to hear that. Let's just turn that up a little bit. You can hear a 300 Hertz tone reset. Now, in the last tutorial, you also learned about envelopes. So let's make an envelope. Now you need to be careful here. You'll see a bunch of different kinds of envelopes turn up. You need to be careful that you select the one that says beads project. Let's just call it envelope with a lowercase e. and we'll make a new envelope, instantiate a new envelope. And again, if you have this help window open, you'll see that there are a number of options here. And the first is just to instantiate a value. I'm going to instantiate that with a value of 0. And I'm actually going to change this name here to call it amp envelope. I'll make that shorter because I'm going to use it to control the amplitude envelope, the amplitude of the output. So what we could do now is take this amplitude envelope and put it in here to control the gain. And so if we start typing that, IntelliJ will recommend it as an option. It's already a unit generator. In other words, this envelope is running at audio rate, and so it's possible to plug it in here as a function to control the gain. If we recompile and play this, we'll wait and see that's recompiled, and play this, what do you think we're going to hear? We have a wave player playing at 300 Hertz. We have an envelope, amplitude envelope. We have a gain object, the value of which is set by the amplitude envelope. We've plugged the gain object, the wave player into the gain object, and then we plug that into the output hardware. In fact, we're going to hear nothing at all because we've set this envelope to a value of 0, and therefore the gain is set to 0. Let's just double check that. Indeed, there it is playing, but it's not doing anything, or it's not sounding. So let's come back in here and add some segments to this. So we're going to have amplitude envelope dot add segment, and then you'll see here that we have a bunch of options. You'll also see those popping up here. And the option that we want is to tell it where we want it to end up. Let's say 0.5, and we'll tell it to go there over 200 milliseconds. So we're now going to have an amplitude fade up on that envelope. Let's continue to add some here because we could think about making, for instance, an ADSR envelope, an attack, decay, sustain, and release envelope. Let's make a simpler one here, which is simply to have an attack phase and then perhaps a sustain phase. So let's add a segment here, and we'll make this stay at 0.5, and we'll make it stay there for 500 milliseconds. And now let's add a release. You'll see that this 0.5 is underlined in red because I forgot to put an F there to indicate that it's a floating point number. So let's make another segment, and this will be our release segment. So we'll go back to 0 over 500 milliseconds. So now we have an amplitude envelope that starts at 0, goes to 0.5 over 200 milliseconds, stays at 0.5 for 500 milliseconds, and goes back to 0 over 500 milliseconds. And note should therefore sound for 1200 milliseconds. So let's compile that again, and then we'll send that off to the simulator. And every time we send that, you can hear the gain coming up, staying there, and then fading out. Okay, so what we've learned previously is that this sound is started here, but it's never killed off. So if we recompile this, leaving the amplitude at 0.5 and send that over here, it'll just play continuously, as you can hear. Okay, so as we can see, that sound now plays forever. So I want to introduce to you the kill trigger. The kill trigger will destroy this algorithm once the envelope is complete. And the best place for us to put the kill trigger is in the last segment of the envelope. Let's take a look at that. So I'm going to uncomment this command / to do multiple lines. And here we have our last segment going back to 0. I'm going to add to this new kill trigger. And what I want to do is I want to kill the last item in the signal chain. And if you think about this, we've plugged the wave player into the gain object and then the gain object into the output of the hardware of the computer. We're varying the amplitude in the gain object using the envelope, but the last object in the signal chain is the gain object. If we kill the gain object, we kill everything that goes behind that, upstream from that. So I want to put G in here for the gain object. If I do that, however, it's going to go red, as you can see here. And the reason for that is that I don't create the gain object until after I've tried to call it. So what I'm going to need to do is to take this line, cut it out of there, and put it after the gain object. so that the gain object has been made and already exists. Now what this means is that this algorithm is going to run only until it gets to the end of this fade out, and then the algorithm is going to be killed. So let's try that. We'll recompile it and send that. And you can hear that sound faded up, faded down, and you can't see this, but in fact the algorithm has now been removed and garbage collected. So we can keep sending them here, as many as we like, and it will actually play them and then kill the algorithm when it's complete. We could of course change the the frequency here using a random object, as you learnt in the last lesson. But let's leave this here at this point. So you'll see here that this says new kill trigger, because we're actually instantiating a new function, the kill trigger, right here within the code. Normally we would create them, as you can see here, with the envelope or the wave player in their own line. But here we're just going to create it here and use it straight away to destroy the algorithm. Okay, great. Now, when this becomes really important is actually when we start using a clock. Okay, if we just make a bit of room here and we type clock timer, you'll see that pops up, and it's actually a template in HappyBrackets that generates an entire function for a clock and starts the clock. So this is a regular clock that in this case is going to be running every 500 milliseconds. You think about that, it's twice a second, so in other words at 120 beats per minute. And whatever code is put in here is going to be run every clock cycle, in this case 120 beats per minute. Okay, so if we take all of this code from down here and we just drag all of that up inside our clock function, we now have a clock function which you can see if you click by this little curly bracket here, runs down to here. And inside there we're creating a wave player, we're generating our envelope segments, creating a gain object, we're playing that and killing it at the end of that cycle. So let's just recompile this and send that off to our simulator. You can just hear the pulses there. Let's make this a little bit shorter so that it's happening within our 500 millisecond frame here. So we'll go up over 50 milliseconds, we'll hold it for 150 milliseconds, and we'll fade out over 100 milliseconds. So now we have a much shorter note. And now you'll hear the individual notes being played, and we'll send that here again. And so here you can hear the clock function playing a wavetable at a frequency of 300 Hertz at a rate of 120 beats per minute. And now you can see why the kill trigger is so important, because if we just kept running this and generating new wave players, new envelopes, new gain objects, over a period of time the computer would just get clogged up, running thousands of them that we were no longer hearing. Whereas the kill trigger kills each of them when they're finished, and therefore we're not building up a lot of rubbish in the background that we're not hearing, and we're saving computer cycles for the things we actually want to do. This is a very quick introduction to two important things. The clock function, which you can get simply by typing the clock timer words, and that'll bring up the template here. And the second really important thing is the kill trigger, which is killing the last object in the signal path, the gain object, so that we're not running lots of software in the background, lots of objects that we're no longer hearing and taking up computing cycles. So to look at these two functions, the clock function and the kill trigger, please open and look at this Melody Maker patch that I've put in here. Now there's a bunch of things suggested for you to look at here. I'm going to skip over those. You can come back to those in your own time. I'm going to show you a couple of things. One is I've used the clock timer template to generate this clock, which again is running at 120 beats per minute. Within here we have our wave player, our envelope, our gain object, and we're playing that out. and you can see here that we're using a kill trigger. Now, what I'd like you to look at is something that we'll introduce in more detail later, and that is the pitch object. So if we want to generate notes, we can use the pitch object, and therefore we can force the frequencies to fit a scale. And you'll see here this function pitch.force to scale. Then I'm randomly selecting a MIDI note number between 0 and 48, adding 32 to that, making sure that's a minor scale, and then sending that out. So let's just have a quick look at making this together. So we're going to go up and make a new HappyBrackets sketch, and let's call this Melody Pitches. Okay, so let's do the things that we know well. We'll make a wave player. I'm going to just call it WP again. New wave player. I'm going to give this a frequency to start with, but we'll change that in a minute. 200 Hertz, and we need to give it a buffer. Okay, let's just give it let's give it saw. We'll make this perhaps more like a bass line. Sawtooth wave is excellent for bass because it has a lot more upper partials, frequency partials in the content. Okay, so now what do we need? We need an envelope. We make sure that that comes from the Beads project. I'm going to just call that E. New envelope. And again, if we make sure that our documentation is open here, we can see what's required there. The envelope just needs a starting value. Let's just start that at 0 again. So it's going to start in silence. Then we need a gain object. And the gain object needs to have the number of inputs and outputs and its value as a starting point. So we just have one input, and we'll set the envelope E as its value. Now we can add the wave player to the gain object, so we'll just go g.addInput WP, and now we will send that out, plug the gain object into the output of the hardware here. Okay, so we have a wave player, an envelope, which is going to control this gain. We have added the wave player to the gain object, and now we've sent the gain object out to the hardware. Okay, so obviously before we use this, we want to add a few more segments to the envelope, and so if you remember, we need probably just to use this 2 floats, which is to set up the number that we want to go to, 0.5, and the time it's going to take to go there, 100 milliseconds. Probably want to add another segment which fades that out to, let's leave it. Let's have a sustain at 0.3. It's going to go there over 100 milliseconds. It's going to stay there, so we need to add a sustain segment, 0.3. We'll keep it there for 200 milliseconds. And then we want to fade it back to 0, and we want to kill the entire algorithm. Remember that we're going to kill the gain object because it's the last object in the signal path, and so in order to instantiate a kill trigger with the gain object, we need to add this segment after the gain object has been instantiated. So E.addSegment, we're going to go back to 0. We're going to go there over, say, 200 milliseconds, and we're going to create a new kill trigger, and we're going to kill the gain object so that the algorithm gets killed. So let's just recompile that and send that off here and just have a listen to that. It's only going to play once. You can hear the sawtooth wave has that buzzy sound. Okay, so the simple way to put this within a clock function is just to write clock timer, which generates this function for us at a 500 millisecond interval or 120 beats per minute, and then starts the clock. So let's take our wave player and everything including our output, and we'll put it inside here and recompile that. And now we're going to get that note occurring every 500 milliseconds or 120 beats per minute. and you can hear that. Let's make the attack much faster because it's a bit slow and sluggish at the moment. Okay. Okay, so that gives you a much stronger attack. Okay, so now we're going to make a pitched note to send into our wave player. So the way that we're going to do this is first of all to make an integer, int, called pitch. And we're going to make a version of the pitch class. You'll see the use of the capital P. And I'm going to say force to scale. And then I could just put, well, you can see here, an integer in there. But I'm actually going to make it slightly more complex here because I'm going to actually generate a random number using the random number generator. And then I'm going to call on that next int. And I'm going to give it a range of numbers that it can call from. So in this case, it'll be from 0 to whatever the top number is. So let's make this 32. So I'm going to give it a bounds of 0 to 32. Now I don't want it playing MIDI note number 0, so I'm going to add here 12, which means that the MIDI note number is going to be between 12 and 12 plus 0 up to 12 plus 32. So we're thinking here more in the baseline kind of region. Okay, and now we need to force that into a scale, and you'll see that if I go pitch dot, we actually get a range of different scales and modes and so on here. So let's force that into a major scale. Just double click on that. So now we have an integer called pitch, which is from using the pitch class, forcing it to a scale, which we just defined here as major, and it's going to be a note between 12, our number here, and 12 plus whatever random number is generated here between 0 and 32. Now, we happen to know that the wave player requires a frequency in hertz. So we need to convert that integer, which is a MIDI note number. So just remember that this is actually a MIDI note number. And MIDI note numbers are between 0 and 127. So we need to convert the MIDI note number to a floating point note number, which is a frequency, in order to plug that into the wave player. So let's make a float here called freq, and we'll again use the pitch class with a capital P, and we're going to use a function called, and there it is, M2F, MIDI to frequency. And that's going to convert our pitch that we've made up here. Maybe we should just call that note. Let's call that note. And note, our MIDI note, into a frequency. So if we feed this note into there, it's going to turn that into a frequency, a floating point number. Now, the value of that is that then we can put that frequency in here instead of having a fixed frequency. And so now every time this clock plays, it's going to randomly select a note in the major scale between the MIDI note number 12 and 12 plus 32, which would be 44. And then it's going to convert that note into a frequency in hertz by converting MIDI to frequency, and then plug that into the wave player. Nothing else has changed here. So let's just recompile that and send that off, and now we're going to hear different actual notes of a scale playing, again at the rate of 120 beats per minute or every 500 milliseconds. And you can hear that they're in the bass frequency range, and you can also hear that this nice gritty saw wave is really kind of punching that out there. So we might say, okay, that's too low, let's bring it up to say 24, and let's reduce the range so that it's only going within an octave, and we'll recompile that. It's still forcing it into a major scale. And just think about the fact that the reason we can do this is that we've just learnt about the clock function, which means that it's regularly instantiating this code and running it at a regular pace. We've learnt about the kill trigger down here. We've also learnt about the kill trigger down here, which is killing off this code every time this envelope finishes by killing the gain object and therefore everything that's upstream from there. So we're not overloading the computer by generating notes. And we just learned about the pitch class, which allows us to force notes into a scale, define a scale, and we're using the random function that you learnt in the last tutorial to randomly generate notes. And then we're using this other pitch function, M to F, which converts the MIDI note to a frequency so that we can plug it into the wave player. And there you have it, a small melody maker using the wave player, the envelope with a kill trigger, the gain, which in this case we're changing using an envelope with a kill trigger in the last segment of that envelope, and then we're just feeding it out as you've done before. Okay, so let's move on to the next section of this tutorial, which looks at sample players. Okay, in this next section we're going to move on to looking at sample playback. In order to start that, let's open the simple patch I've given you called sample 1. There are some important things to notice here before we start building our own patch. The first is that we need to define the sample that we're going to play. And you can see here that this is a sample class and that we use the sample manager class to define a string which defines the sample, the directory to play that sample. Then we're going to create a sample player, looks very much like the wave player that you've already used, and we're going to feed it as an argument this sample S. We can then set the loop points, although we don't need to do that initially. And then we're going to set a gain object. You know about that. We're going to plug the sample player into the gain object and plug it into the hardware. So let's just compile this without looping and send it over to the simulator to have a listen. And there we hear a single A on a nylon string guitar, a clean single note played. And it's going to play right through to the end of the sample. Now, an important thing to know here is that when looping is not on, it's not set to loop, then the sample player will kill itself automatically at the end of the sample, because it knows when the end of the sample is, and it knows that it doesn't have to do anything after that point. So it kills itself and the code is gone. When we set looping, of course, it no longer knows when we don't want it anymore. So therefore it's going to continue to play forever, even if we can't hear it, unless we use the kill trigger to kill it off in exactly the same way that we did in the wave player version. Okay, so let's go and make sure that we're in tutorial 2. Let's go and do new HappyBrackets sketch. Let's call it sample test. Okay, so here we have a HappyBrackets action. So as we saw before, the first thing we want to do is call the sample class, and you can see that that's a class because it has a capital letter. And we're going to make a sample. I just called mine S before, but let's call it sample. Let's call it sample 1 so we know exactly what it is. And now we're going to have to call the sample manager class. And you can see here a number of different things coming up, sample manager. And we're going to call the sample function within there to define a sample. And you'll see here it pops up and tells me, okay, you need to put a string name in there. Now, how do we find this long convoluted name that we had here, this long string here? So, it's very cleverly set up here in the HappyBrackets project path within IntelliJ, so that the code that you write here, when transferred to the Pi, the Raspberry Pi, looks in exactly the same places and it all works perfectly on the computer, on the Pi. It's a great thing. So if we look in here, we see data, audio, nylon guitar, etc. And if we look over here in our project path, we'll see a folder called device, and inside that we'll see HappyBrackets. If we open that, we'll see that there's a folder called data, and if we look inside there, we'll find a folder called audio, and all of this stuff is going to be on your Pi as well. And when we look in there, we'll see a number of audio file folders with audio files in them. So here's nylon guitar. It says nylon guitar here, and if we open that, we can see clean A harmonic. And so that's the path. So how do we get this long string? Well, if you're good at doing this kind of thing, you can already type that. I'm not, and I often make typos. So the easiest way for me to do it is to right click on here and then go down to Reveal in Finder. That will bring up that exact sound file in the Finder. Now, if I go and open the terminal, let's just look up the terminal, and drag this file, in fact, let's choose a different one, D, in here, it will tell you the path to that file. And if we look here, you can see device, HappyBrackets, data, etc. And we happen to know that we need this section of that data. We happen to know that we need this section of that path. So I come in, select that, copy it, go back to my patch. Let's go back to the one that we're writing. And then in here, we need that to be in quotes. I can copy and paste that path in there. So let's say that we wanted, let's just do that again. Let's make a second sample. Okay, sample, I'm going to call this sample 2. Again, we're calling up the sample manager, and we're calling the sample function in there, and then in here we need to put in a string, right? So let's go and look at drums. So again, I'm going to right click on here, I'm going to go down to Reveal in Finder, here's the drums. So let's just grab a pattern out of there, let's say 105, I need to just return here so that I start with a new pattern, 105, which is going to be a drum pattern playing at 105 beats per minute. I'm going to copy everything here back to data. So I've got data, audio, drums, 105, and I'm going to go back to my patch and I'm going to paste that in between the two quote marks, like so. And so here you can see data, audio, nylon guitar, etc. In what we just did, we start off with data, audio, nylon guitar, here, data, audio, drums, 105. So we've just defined two samples that we could play. So the next thing to do here is to create a sample player. And let's just take the suggestion from IntelliJ and call it sample player, and we need to instantiate a new sample player. So we're going to say new sample player. And now we need to feed it the sample player. So we need to tell it exactly what we're doing here. And what we're doing is we're sending it this sample buffer, the string that tells it exactly where the sample is. So we could send it sample 1 or sample 2. Let's send it sample 2. Oh, I misspelt that, as you can see. So let's just correct that. Sample 2. Okay, sample 2. Just so we've got something a little bit different from the guitar note that we had before. So now we've got a sample player which is going to read sample 2 and play that. Okay, a useful thing to do here is to work out how long the sample is, especially if you're loading different samples in at different times. And in a little bit we'll look at making groups of samples, in other words, whole folders of samples that we can randomly call up different samples as we go along. So if we just make a new float here, I'm going to call it sample length, and I'm going to get our sample, in this case sample 2, and I'm going to run a function called get length. And you'll see here that it's going to complain. It's going to say that get length is not a float, and we need to cast it to a float. So we'll take that suggestion and cast it to a float, and it'll put a float in front there. So now we have the sample length. Okay, so let's make our gain object. We need the number of inputs and outputs, and then we need the gain value. So there we have 1. We could make it 2 if we want it to be stereo. So let's go back here, make that 2. So let's go g.add input, and we'll add our sample player in there. And let's go hb.sound G. So this is all very familiar to you. So we're going to put the gain object out the hardware. So let's compile that, recompile, and send that off to the simulator. And we should hear a drum pattern. And indeed we do. It's going to play through to the end of the drum line, the drum sample, and then it's going to kill itself. Okay, so the next obvious thing that we could do here is actually to add looping. Okay, so let's go up here after our sample player and set that looping function. So we're going to call our sample player, and we're going to put in here set loop type, and we're going to need to call that, and you can see that already being defined over here, from the sample player class. So we need to start again by typing sample player, and here you can see sample type, loop forward, loop alternating, which means play forward, play backwards, etc., etc. Let's do alternating, because then we'll hear the loops, because it's going to play the sample forward, and then it's going to play it backwards, and then it's going to play it forward again. Okay, so now we've got a looping sample. It's going to continue to loop, and now remember that it's not going to kill itself. It'll just keep playing backwards and forwards forever. Now it's going backwards. Now it's going forwards. Okay, so in order to make it play forwards, forwards and backwards, we need to keep the sample alive for 4 times its sample length. We calculated the sample length here already, so that's going to come in very useful. So we need an envelope. Again, we're going to use this envelope, just going to call it E, new envelope. I'm going to start it with a value of 0. And now we can add segments to that. So let's go E add segment, and we'll go to 0.5 in amplitude, and let's do that over the sample length just to make life really easy. Then we're going to do exactly the same thing. We're going to stay at that segment for, which is 0.5, for the sample length times 2. Oh, sorry, should be sample length times 2. In other words, it's going to fade up over 1, and then it's going to stay at 0.5 while it goes backwards and goes forwards again, and then we're going to fade out as we go back. So we're going to add another segment here, and we're going to go back to 0 over sample length. Okay. So then we've got 1, 2, 3, 4 sample lengths. Okay, we're going to go forwards, backwards, forwards, backwards. Okay, that means that in this segment we actually want to kill this. So let's go new kill trigger, and we want to kill off the gain. Now, as we've seen before, we can't place this argument here because the gain is not made object until there. So we need to take this line here and drag it down after the gain object has been created. Okay, so let's see what happens. It should now play our drum loop 4 times. Forwards, backwards, and finish. Now, in order for that to work, we need to take our envelope here and actually apply it as the gain here in our gain envelope. So let's recompile that and play it. So it's fading in, backwards at 0.5, forwards again at 0.5, and then fade out as it goes backwards and kill itself. Okay, so now you've seen a simple application of the kill trigger to the sample player, and we need to use it whenever we're using looping on the sample player. Otherwise the sample player just keeps playing ad infinitum. You also just saw how to use the terminal window in order to get this long string that you need here in order to define your sample. And you'll see here that we've basically used this envelope to establish the number of times the sample plays, and we did that by calculating the sample length by taking, in this case, sample 2 and using this function getLength in order to give us a number that tells us how many milliseconds that sample is in length. You'll see that sample 1 is grayed out here, and that's because we're not using it at this point. So maybe we should do that. So let's go down here and make a new sample player, and we'll call this, what will we call it? We will call it sample play 2, and we'll make a new sample player, and we will, a new sample player, and we will give it sample 1 as the sample that it needs to play. Okay, now that's just going to be a clean single note, okay, and then it's going to complete. Okay, so now let's make a gain object. I'm just going to call it G2 for speed equals new gain object. We need to tell it the number of inputs and outputs, and we need to tell it the amplitude that we're setting it at. So let's take G2 dot add input. You know all this stuff very well. We're going to give it sample play 2 as its input, so it's going to take the second sample player, and now of course we're going to plug this into the output. Okay, so this will play one round of this clean guitar, and it's going to play at an amplitude of 0.6 and out through the same hardware. So I'll just say here, play the second sample. Okay, cool. So let's recompile that. And it compiled fine. Let's send it off. Okay, so let's reset that. So let's actually turn down the drums a little bit. Let's put that at 0.3, 0.3. Okay, so let's put our guitar sample in a clock function. So we'll use the clock timer function that we've used previously, and again its default is set at 500 milliseconds, so at 120 beats per minute, and then the clock is started here. We're going to take all of our second sample player and we're just going to pop it inside the clock. So what's going to happen now is that that sample is going to be played again and again every 120 beats per minute. Let's start that. Recompile and send it off. Okay, so something interesting just happened. Let's see if you can pick up what that is. Send it again and listen to the drums. Okay, so the drums seem to stop. Now the reason that the drums stop is that this function, hb.sound, as you learnt in tutorial 1, also has polyphony management. So once it gets to 4 voices playing, it kills off the first one. So when it gets to the 5th one, it kills the first one. The 6th one, it kills off the second one that was instantiated, and so on. So there are only ever 4 sounds generated at any one time. So that might be fine for the guitar note, but it's not fine for the drums because we want the drums to just continue on in the background. Okay, so what we're going to do here is slightly different. We're going to use a function that connects the drums, our first sample player, to the audio hardware output without any polyphony control. So we need to connect to the HappyBrackets context, and then we're going to type get audio output. Then we're going to type add input. We're used to doing that in the past, and now we're again going to add gain there. So this function, get audio output, in the HappyBrackets action context is not polyphony controlled. So let's just recompile that and see if that fixes our problem. And as you can hear, the drums are still playing whilst the guitar notes continue to play. Let's slow the guitar notes down a little bit, make them at 60 beats per minute, in other words, once every 1000 milliseconds. Now, I want to introduce you to one further thing before we move on, and that is that it's possible to adjust looping points here. It's also possible to adjust the pitch or the playback rate of the sample. I'm going to let you explore looping points yourself, and we'll cover that a little bit in the Granular sound sample player. But let's just look a little bit here at the playback rate. So I'm going to generate an envelope, and I'm going to call it E-rate. Oh, don't need cap lock. So equals new envelope, and of course we need to give it a starting rate. So I'm going to give it a starting rate of 1, which would mean that the sample will play back here at its normal playback rate. Now then I'm going to add a segment that goes to 1/4 of its playback rate over 100 milliseconds. We want to do this quite fast because the guitar note doesn't sound for very long. And then I'm going to add another segment which goes to double the normal playback rate in 200 milliseconds. So we're going to start at the normal playback rate. Quite quickly we're going to go down to 1/4. In fact, let's make this a little bit slower so you can hear that. And then we're going to go up to double, and then let's bring it back to normal playback rate. So we're going to use this to control the playback of the sample itself. And so what we're going to do here is we've got our sample player, and we're going to go sample play, which is play 2, sample play 2 dot set pitch. So we're going to set the pitch of playback, and we're going to set that with the envelope that we just made E-rate. So we're going to have the pitch go down, up, and back to normal. Okay, and that's going to happen every time that this clock. Okay, what have we got here? Incompatible float. I forgot to put F here to make that a float. So let's just recompile that and send that over. And now every time the guitar note plays, which will be once every second, you'll hear the pitch vary. You can hear it going down, up. Okay, so of course we could change that. Let's make it go up to 2. Let's make that over like 500 milliseconds, a bit slower. Down to 0.2 over 200 milliseconds, and then back to normal playback rate over 500 milliseconds. Recompile. Now it's going to go up and down. Etc. So this is using an envelope to change the rate of playback. Equally, you could use an envelope to change the loop and start points dynamically and be scrubbing through the sample as it's playing back. Okay, so we can change the loop points, and equally you could use an envelope to dynamically move the start and loop end points. And you can do a bunch of other things here. We'll get into the loop points a bit more when we get to the Granular patch. Now, one final thing that I want to look at here is how we select samples. So here we've defined just 2 samples. But I mentioned earlier that we could define a group of samples, and it would make sense here if we defined the guitar notes as a folder of samples of different pitches, and then each time called a different pitch to play. So in order to do this, we need to make a group of samples. And we do this by making the sample manager, taking the sample manager and calling group on that. And then that's going to require that we give it a couple of strings. The first string is the name of the group, and so we're just going to call this guitar. And then the second string is actually the directory to that folder. So let's scroll back up here to nylon guitar, and we will again go and reveal that in the Finder. Oops, there we go. And let's just clear out here. Here we go. So where are we? Nylon guitar. And we'll just copy that. So we want data, audio, nylon guitar. We want the folder, not the name of the files within it. And so again, we'll put that in here. Okay, and so now we have a sample group, which is actually the entire folder collection of guitar sounds. Okay, and so when we go down here into our clock to play our sample, instead of feeding it a single sample, I'm going to actually do something slightly different. I'm going to call up again the sample manager. Okay, so now instead of calling the same sample every time here within our clock function, I'm actually going to call a different one randomly from the group that we just created. So before we actually make that, let's just make a new sample here. Okay, and I'm just going to call this S2, just as shorthand. And we're going to call the sample manager again. And then we're going to go random from group, and we're going to tell it the group that we're working from, which is the group that we set up here called guitar. Okay, now we're going to plug that sample in here, and so each time this clock is called, we're going to create a sample which is randomly selected from our group of guitar samples. So now we're going to get different notes each time the clock plays. Oh, what have I got? Expected. Okay, I forgot the semicolon at the end there. Easy to do. I'm sure you'll do that too. Okay, there we go. Let's have a listen. Okay, so let's just reset that. Just out of interest, let's take out our envelope, and we'll just set the pitch back at 1, which is the normal playback pitch. And okay, we'll recompile and play that, so you'll just hear the notes at the normal pitch instead of okay, what's going on here? Oh, that needs to be, sorry, we won't set the pitch at all because it won't take 1 there as an argument. It needs to be actually a U-gen at audio rate. I could do that just by setting this at 1. In fact, yes, let's do that. So we'll put that back, and we'll actually uncomment that line, which is where that is set first at 1, and we won't change it here. Okay, so recompile, and we'll send that over. And now you can hear the individual pitches being played against the drum line. Of course, the drum line is playing at 105 beats per minute, and the guitar is playing at 60 beats per minute. Of course, we could change that if we wanted to. You'll also hear that the drums stopped after this envelope segment had played the drums through 4 times. Okay, so what you've just learned is how to define a single sample using a string here that defines the actual file that's been called to play. We've also learned how to use the sample manager, and here you'll see this is set up slightly differently because it's creating a background collection of sounds rather than defining a single sample. How to define a group of samples that have been called here each time. We've learned how to set up looping on the sample, and we've also learned a little bit about a different option here for outputting the audio to the hardware, get audio output, and this function doesn't do polyphony management. We found previously that if it did, after 4 guitar notes have been, or 3 guitar notes have been played here. On the 4th one, the drums disappeared because they were the first voice to start. Then we also looked here at using this sample group in the guitar and using this function random from group in order to call different guitar notes from that collection of samples. That collection of samples could be as big as you like, and it could be anything, of course, a collection of percussion sounds, bird calls, it doesn't really matter. We also looked at the function here to set the pitch of playback of the sample, and we talked about the fact that we could also set the loop start and loop end points here, but we're not going to go into that at this point. So that brings to a close this section of the tutorial on the sample player, and then we're just going to finish off with a little treat looking at all of this same code, but just by changing sample player, where is it? Sample player here to granular sample player. So let's do that in just 1 second. Okay, so we're just going to finish off this tutorial by looking at the granular sample player. Normally a sample is played through by reading each sample in the audio and just playing it one after another. In granulation or granular synthesis, what happens is that the audio is kind of smashed apart into little segments called grains and then reconstituted based on a number of variables. Things like the grain size, the grain interval, which is the amount of time between each grain, and so on. So let's have a look at a few of these things. The first thing to do is to extend this patch that we already have so that instead of just having a sample player, we have a granular sample player. We can just do this by starting to type grain here, and we have granular sample player. Now we need to make a new granular sample player. Now we could play this at this point and absolutely nothing will have changed because it's still called sample player here, and everything that happens here will be the same, etc. Sounds a little bit different going backwards. Okay, let's start by also turning down the guitar here quite a lot. So it's just in the background. Okay, so let's actually just call this, properly call it granular sample player so we know what we're talking about. Okay, oh, that made a horrible mess. Okay, so I'm just going to show you a better way to do that. So we want to change this name. So if we right click on here, we can actually go refactor, rename. And now I'm going to select here granular sample player. So it's going to, you'll see that it's found every place in the code where sample player occurs. And now if I double click on granular sample player, it's changed its name here, but it's also changed its name everywhere else that it occurs. That's super fabulous in IntelliJ. And you could see that as I started to just type to change the name earlier, I started to get a mess in the code. Okay, so now the first thing that we might start to do here is to think about setting loop start and loop end points. We can do that because we already have looping set here to play alternatively forward and backwards. So I'm going to use envelopes to set these variables because I need to have a ugen or an audio rate function establishing those. So I'm going to start this as loop start, new envelope, and I'm going to give it a function of 0 because I want it to start at the beginning of the sample. But let's change that. So loop start.add segment. And now let's change the sample start point to say halfway through the sample. Now we can do that because we've actually already calculated the sample length here. So we need to do this after that. So let's just put that in there. So we've already calculated the sample length. So let's set it to sample length times 0.5. So that means that the loop start point is now going to be halfway through the sample. And we'll do that over the duration of the sample length. In other words, it's going to move the beginning of the sample, the loop point, from the beginning of the sample to halfway through the sample during the period that it plays the entire sample. Okay, and then it's going to stay there. So the loop point is going to be halfway through the sample. Okay, so let's set a loop end point as well. Okay, and now we want to set this as the end of the sample, so the obvious thing to do is to set that at sample length, because again, we know how long the sample is. Okay, so let's change that though. Let's take loopend.addSegment, and what we might do here is to set that to sample length times 0.75. So we're going to have a quarter of the sample playing from 0.5 to 0.75, and we'll do that over the sample length. Let's do that over sample length times 2. So it's going to change slowly. Okay, so we've established an envelope to set the sample start, and we've established an envelope to the loop start, and established an envelope to set the loop end. Now we have to actually apply these here. Okay, sample length with an F for float. Okay, so we need to take our granular sample player, and then what we need to do here is to set the loop end or the loop start. In this case, we want to set the loop start, and we're going to set that loop start to be the variable, the envelope that we just made called loop start. Equally here, we want to set the granular sample player set loop end, and we're going to set that to be loop end. Okay, so now if we play this, we'll hear that the loop start point moves from the beginning of the sample through to halfway through the sample over the length of a sample and stays there, and the loop end point moves from the end of the sample down to 3/4 of the way through the sample and stays there. Remember, we're playing this backwards and forwards 4 times, so you should hear some variation in that. So let's recompile that and send it off to play. And you can hear that loop getting much shorter. Okay, so that's quite interesting. So now we have control and dynamic control using an envelope of the loop points. So there are a couple of other really interesting things to look at here. One is the grain size. So let's start by making another envelope and call this grain size. And I'm just going to start by making this with a fairly long grain size, 800 milliseconds. So let's take the grain size and add a segment to this. And what we're going to do is reduce it to a much shorter period, like 60 milliseconds, a much shorter grain size. And we'll do that again. Let's use the sample length times 2. So by the time it's played through and played back, as it goes to go on the next one, the sample length is going to be much smaller, the grain size is going to be much smaller. Now, of course, again, we need to actually apply that. So we're going to set grain size, and we're going to set that with that envelope grain size. And as you might have guessed, the other really interesting thing to do here is to set the grain interval, which is the amount of time between these grains. So let's make another one. We'll call this grain interval. Oh, sorry. And I'm going to start by setting this at about 120 milliseconds. We've got long grains, 800 milliseconds in the first place. And so if we set the interval for each of those at 120, there's going to be lots of overlap. Okay, and then we're going to grain interval. We'll change that. We'll add a segment, and let's make that really short so they really overlap a lot. Because we've also changed the actual grain size itself. And let's do that over, say, the sample length times 2, so that we can hear that gradually changing. Again, we need to apply that to our granular sample player, so we're going to set grain interval, and we'll call that grain interval. Okay. And so here we've set the start of the loop, we've set the end of the loop, we're changing those dynamically. We've set the grain size, we're changing that dynamically. We've set the grain interval, the period between the grains, and we've set that dynamically. Let's have a listen to that. recompile that and send it off to play. Right, you can hear those grains getting shorter, really short grains. So this is where you can see that granular synthesis starts to produce effects that are really interesting, and you get all of this kind of gnarly edge to it. I want to do one more thing here, and that is that I want to actually produce a sample group from the drums. So let's go to manage, sample manager dot group, and we'll set up a group called drums. And so we need to go and find out exactly where that is. And so let's go back to our terminal and we'll go and find the drums. Here they are, drums. Drag it on there. And so we need data/audio/drums. Some of you are going to be much faster at just typing that. It's much easier for me to go find it and paste it in there. Okay, so here we've generated a sample manager group called drums. We need to put a semicolon at the end there. And now we want to randomly call those samples, those drum samples, every time our clock generates a new granular sample player. So let's, instead of sending this as set sample, I've just deleted that, we need to make a sample here. So we're going to make a new sample and we'll call this drum sample equals sample manager dot random from group drums. Okay, so our drum sample is going to be randomly selected from that folder. Now for our granular sample player we need to give it that sample, drum sample. Equally down here now you can really see the value of generating or calculating the sample length each time. We want to actually calculate the sample length of our drum sample, get length. And we want to do that because each time one is randomly called from the folder, it's going to be a different length. And so then all of these calculations, because we're using the sample length in all of these calculations, will be custom made to that particular sample. Okay, so let's recompile this. And remember, we've commented out the guitar, so we're not going to hear that. And let's send that off to play. And now you can hear it selecting different samples. And we're getting quite a crazy collection there. Okay, obviously if we ran much shorter samples, let's do that, much shorter grains, and started with a shorter grain interval. No, let's leave it at about that, but maybe go down to the shorter grain interval over a shorter period of time, you're going to hear here even more chaos. And remember, each sample that gets called gets started to play at the beginning of the loop at a normal rate. Okay, and just because we can, let's do that at 120 beats per minute and leave it there for today. So you've learned a whole bunch of stuff today about setting up samples, individual samples, groups of samples. You'll note that both of these samples are grayed out at the moment because we're not using them. You've learnt about the sample player, but also the granular sample player. And then you've learnt that within the granular sample player, as we can do in the sample player, we can set loop start and loop end points. But in the granular sample player, we can start to set grain size and grain interval and other variables to really get interesting effects happening within that. And so on that note, at 120 beats per minute, I'm going to play some crazy drum samples doing crazy granular stuff. Thanks very much. See you next time.